Advanced Algebra Chapter 7, Lesson 6. And before we look at composing functions, I want to review a little bit about function notation. In function notation, we replace the y value with what we call function notation. And we use a letter, f of x. And this variable that's in here is the variable of the function. So we want to remember that. That tells us what the function y, or what the value y is a function of. So we replace y with f of x would be equal to 4x squared plus 3. And if I wanted to replace this wouldn't be g of x, but it would be g of a, because a is the variable of the function. And this might be h of b, because b is the variable in the function. So function notation simply replaces the y value with this function notation. Further then, if I want to evaluate the function with something, in other words, I want to substitute a value in, I can say, okay, if f of x is 4x squared plus 3, what would be f of 2? Meaning, I now take this 2 and put it in the place of the x. So this would be 2 squared plus 3, and then I would simplify. Or if I wanted to know g of negative 7, that means wherever there's an a, I'll put in negative 7 plus 4. Or I could put anything in there. So if I just wanted to do h of cat, then that would be cat in wherever there's a b, so cat plus 7. So function notation allows me to rewrite the letter y in terms of a function notation, this being the letter or the variable of the function. And then by using this notation, I can tell whoever is looking at the function what I want them to substitute into the expression. Okay, so that reviews a little bit of function notation. Now let's look at composing functions. When we're composing functions, it's a different way of combining functions. It's not an algebraic method. We're not adding, subtracting, multiplying, or dividing. We're actually taking one function's output, its y value, and substituting it into the next function's as the next function's input. So we take an x value, we substitute it into one function, say an f function, that produces a y value, or an f of x value. We then take that y value and put it into a separate function, the g function, and then that produces another g of x value or a y value. And when we put one function's output into another function, that's called composing function. Composite meaning to put together. So this is what composing function consists of. We take the output of one function and then it becomes the input of the next function. The notation that we use is this little circle, and this means f composed with g of x. And what that means is f of g of x. Now remember about the function notation we just talked about. Whatever is here is what we actually put into the f function. So g of x represents the y value produced when I put an x value into the g function. I then take that y value and put it into the f function. Now what I want you to notice here is that the second functions is the one that goes into the first. So this produces the y value, which then goes into the other function. So we use this little circle, it means composed of, and we read it f composed with g of x, or g composed with f of x. This is sometimes known as Fagengoff. Okay, Fagengoff. My uncle is Fagengoff from Sweden, yes. Okay, so anyways, so in this function, I'm taking the g function and putting it into the f, and for this expression, I'm putting the f function into the g. Okay, so let's look at an example. There are two methods for doing this, meaning I can either substitute the entire function into the other function and then simplify, and then simply plug the value into the composed function, or I can put the value into the f function or the second function first, calculate its value, and then take the result and put it into the first function. Either method will produce the same answer. In other words, if I choose this method, before I substitute in any value, like negative 5, I'm going to take the entire function and put it into the other function. In other words, because I'm composing g with f, that means the f function goes into the g. So I'm going to take this entire f function and substitute it in for x. So wherever I see an x, I'm going to put in x minus 2. So x minus 2 goes into the g function. That means x minus 2 squared. Once I've done that, then I'll go ahead and substitute the negative 5 in and simplify. So negative 5 minus 2 is negative 7, and that squared would be 49. That's composing a function with another by substituting in the entire function. In the second method, I simply take the negative 5, substitute it into the f function, and then take its result and put it in the g function. So the f function is x minus 2. So I put in negative 5 minus 2, that gives me a negative 7. Then I take that negative 7 and put it into the g function, which is x squared. So that gives me negative 7 squared, which is 49. So it doesn't matter how you do it, substituting the value in or substituting the function in, both methods will produce the exact same value. Before we look at a few of examples of composing functions, let's look at answering this question. Is composing functions commutative? Meaning, does the order in which I compose them make a difference? If I compose g with f, does that or will that produce the same answer as composing f with g? So let's take a look at an example and see if we can't answer that question. So let's say we have a function f of x, x minus 2, and a function g of x, x squared. Will it make a difference if I have g composed with f or f composed with g? Well, if we do g composed with f, I take negative 5, substitute it into the f function, so that's negative 5 minus 2, which is negative 7, and now I take that result and put it into the g function, so negative 7 squared is 49. Now let's say I reverse the order. Let's put negative 5 into the g function, so negative 5 squared is 25, and now take that y value 25, put it into the f function, 25 minus 2 is 23. So you'll notice that this is not commutative. I do not get the same answer when I switch the order. So it's very important to know that when we're composing one function with another, the function that comes second must be evaluated first, or I have to substitute into that function first, and the result of that function is then what gets substituted into the first function. So our two functions here are g of x is 2x and h of x is x squared plus 4. If I'm composing h composed with g of 1, I take the number 1 and put it into the g function and take that result and put it in the h function. So substituting 1 into this value or this function, 2 times 1 is 2, I then take that result, put it in the h function, 2 squared is 4, and then 4 plus 4 is 8, so h composed with g of 1 is 8. Okay, let's look at h composed with g of negative 5. Again, the second function is what I evaluate first, so negative 5 into the g function is negative 10. I then take that result, substitute it into the h function. Negative 10 squared is 100 plus 4, so that would be 104. Now, it doesn't matter what the functions are, we simply follow the method. Meaning, what if I have a function composed with itself? Well, that simply means take 3 and evaluate it into the g function, so substitute it into the g function. So 2 times 3 is 6. And now take that result and plug it into the g function. So I put 6 in. 2 times 6 is 12. So whether I'm composing a function with itself or composing one function with another, it doesn't matter. Simply make sure that we take the second function and substitute it into the first function to evaluate the expression.